Okay, welcome to another lecture on basic surveying. This is module number 5 and this module is on theodolites and total stations. Today we will do lecture number 3 of this module. Now what we have done so far as this module is concerned on theodolite and total stations, we have seen the instrument, the theodolite, why we need to use it, and in particular in our last lecture we discussed about the telescope which is used in the theodolite and then some definitions like the line of sight, line of collimation and some more definitions which are related to the theodolite. We also saw what is face left observation, what is face right observation. Then if you are going to a field and we want to measure an angle, we saw the procedure last time. So there are some steps which we need to do at every station. These steps are called temporary adjustments. What we do, we take the theodolite along with the tripod to that particular point, or we can say survey station. Then we need to do couple of things. Number one is centering. We put our tripod over that point, approximately center it. Leveling, we level the tripod head approximately. Then having done this, we put the tripod or we put the theodolite on top of the tripod, and after that we start doing the centering of the theodolite, leveling of the theodolite, and as well as we do the focusing. So having achieved proper centering and leveling, the focusing means we sight to the object and we need to focus that. In order to focus the object, we need to first focus the eyepiece so that we can see the crosswires very distinctly. Then the image through the objective lens is focused on the plane of the crosswire. Now here is a term which is called parallax. Parallax means if this is the plane of the crosswire, the image which is being formed is not at this plane but rather here. Well, you may find this is clearly seen, the image is distinctly seen, focus image as far as your eyes are concerned, but is there any parallax between them? Yeah, there is a parallax between them, because if you move your eyes here and there slightly, you will find there is a relative displacement between the image and the crosswire. If these two are exactly on the same plane, so the image has been formed on the plane of the crosswire. Now by moving your eye here and there will not be any relative displacement between these two objects. Between these two objects means the crosswire and the image. So the meaning is we have removed the parallax. So we remove this parallax and now we are ready to take the observations. So we have seen that thing. Then also we saw the method of repetition. How we can measure a single angle using the method of repetition. In the method of repetition, if you recall, we use the theodolite itself for mechanically summing up the angles. One single angle was measured time and again, and only the first reading and the last reading after n number of iterations they were recorded. And then finally we take the average of, or not average I will say, rather we divide the total reading divided by total number of the iterations. How many times we took the observation. And this is how we can improve the precision of the instrument also. What we are going to do today, we will look into another method, which is the method of reiteration. Another method useful in some other circumstances. Then we will compare these two methods, the method of repetition and method of reiteration, for the accuracy which they can give. Then we will also see the vertical angle measurement and possibly some errors of the theodolite, which are because of the person involved, the natural errors and the instrumental errors. And finally, if time permits for this video lecture, we will also go into fundamental lines of a theodolite, what these are. So we will start now with method of reiteration. Okay, in the method of reiteration, what we do, if for example there is a point O where the observer is, we have some ranging rods, for example one here at P, at Q, at R and at S. Okay, So we are interested in measuring the angles between all these points. So the angle we can say theta 1, theta 2 and theta 3. We are interested in measuring these angles. What we can do, we can go by the method of repetition and we can measure these individual angles separately. But in the case of the method of reiteration, which is also called method of direction, the procedure is slightly fast. Whenever we need to measure multiple angles at a single point, as in this case, we need to measure at O 3 angles. So we generally go for method of direction or method of reiteration. What do we do in this case? The procedure is simple. Again, we will take our theodolite to the point O. Well, the theodolite is set at O. We will make the reading in the theodolite 0, 0, 0, 0 degree, 0 minutes and 0 seconds. You know how to do it now. Once we have done it, we will unclamp the lower screw and we will rotate the theodolite or the telescope. So by unclamping the lower one, and while the upper one is clamped, the reading is not changing. It still remains 0, 0, 0. So what we will do, using that, we will first bisect P. So the P is bisected and the reading is 0, 0, 0. Next, we bisect Q. Next, we bisect R. Next, we bisect S. And we keep taking all these observations, all these readings. The reading at P was 0, 0, 0. At Q, whatever is the value. At R, whatever is the value. Similarly, at S. Then next, what we do? We close the horizon. The meaning of that is, after taking this reading at S, we close the horizon and we come back to P again. So while we are coming back to the P again, the reading should be 0, 0, 0, as we had initially fixed for the point P. It might not be so also, depending the errors in the theodolite, or maybe while you are working, you mishandled some of the screws a little bit, which will say slip of the screw. So because of these reasons, the reading may not be 0, 0, 0. It may be 0 degree, 0 minute and 20 seconds. So what is the meaning of this? While we are measuring the angle theta 1, theta 2, theta 3 and this total angle, we introduce an error equal to 20 seconds. So in method of direction, method of reiteration, what we do, if this error is small, as in this case, and of course depending upon the kind of the survey we are doing, if it is small, we distribute it, 20 seconds can be distributed in theta 1, theta 2, theta 3 as well as in angle S, O, P. So 20 seconds divided by 4, 5 seconds. So we will distribute this 5 seconds to each of these angles. So we are correcting our observation for this misclosure. Now this observation can be taken right now. For example, let us say we are doing it on face left. You know now what is the meaning of face left and face right observation. We can do the same thing on the face right also. For example, let us say right now we are doing it on face left. So we started from P, went to Q, went to R, went to S and closed it. Then what we can do, we can change the face now and we can repeat the same procedure. So we will have readings or angle values for face left and face right. Now how to record these readings, how the tables look like. I am going to show you the tables now. So the table looks like this here, and in this table, as you can see, once we start taking the observations from P, whatever was the value at P, it was 0, 0, 0. This is the table for face left, and we are swinging the instrument to right. Well, what we write, the first column is instrument at, because the instrument is at O. Then we are citing to number 1 P, so the readings were 0, 0, 0. Now this is for vernier A, and for vernier B we will write only in minutes and seconds. So 0 and 0 if it is so, and then the mean of vernier A and B, which is 0, 0 and 0. Then our next sighting is to Q. So whatever is the value at Q, for example 30 degrees, 20 minutes and 20 seconds, and here it may be 20 minutes and 40 seconds in vernier B. Well, we will take the average of these two, so 30, 20 minutes and 30 seconds. Now what it gives you, we can similarly write the observations what we are recording for R and for S also. And finally, when we close the horizon, as we go back to the P, we will again record the reading here. Maybe this reading is 0, 0 and 20 seconds. Well, there is some error, 0 and 20 seconds. So there is some error of 20 seconds is the error of misclosure. So this will be distributed. Now what we can do, using these values here, using these values we can determine the value of the horizontal angle. I can write the horizontal angle, the reading to Q minus reading to P will give me the angle here, which will be 30, 20 and 30. Similarly, we can get these values of the angles also. So all these angles are written here. Now so far in these horizontal angle, the correction has not been applied for the misclosure. What we can do, we can apply the correction for the misclosure, as we found it should be 5 seconds to each of these angles, and we can write these corrected angle values over here. So this is one face left reading. What we can do, we can have a similar table for face right. We are swinging to left now, and by doing the same procedure, nearly same, we are getting the angle values again for face right. So we have the angle values of the horizontal angle for face left and face right, and finally we will take the average of these two, average of face left plus face right by 2, and this is what we will write in the final values of the angles. So this gives us finally the angle values by the method of reiteration. And whatever we have seen right now, this entire thing is one set. So this we say the face right observation, all this constitute to be one set of the observation. We can have multiple sets, 4 sets, 5 sets, depending what kind of survey you are doing. Okay, in order to measure the angle, as we have been seeing that what we need to do, we need to bring our tripod and the theodolite and we need to center it. As in this diagram, we wanted to keep our theodolite exactly over the point O. There in the ground, point O is a point, and what we want to ensure that the vertical axis of the theodolite, we have seen the vertical axis of the theodolite about which the theodolite rotates, should pass through the point there on the ground. Now this is slightly difficult exercise, difficult in the sense that a lot of trial and errors are involved, and never we can reach the true value or the true orientation, true centering, perfect centering. So what to do in that case? We should know if at all we are introducing some error due to miscentering, what kinds of errors will be propagated into the angle that we measure. So this is what we are going to see now. We are going to see error in angle measurement due to miscentering. So basically if I draw the diagram here, what it is like, let us say there are 2 points P and Q, and O has to be here, this is the observer, and we want to measure angle theta. The meaning of miscentering is somehow we are not able to center our instrument at O, rather we are centering at O dash. Now because of this, what will happen, instead of taking OP and OQ as the line of sight, we will be taking O dash B and O dash Q as the line of sights. So what we are doing, instead of measuring theta, we are measuring phi. So this error E in angle due to theta minus phi, or we can say due to this miscentering is the error introduced in our angle. So we can see by this simple diagram that whenever we are measuring the angles, and if there is miscentering, there is some error which is going to be introduced in our angle measurement. Because there in the field, what angle we need to measure? In the field we need to measure theta, because the angle in the field is theta. But what we are measuring phi, and because of this there is an error of E here. Now what this E will depend upon? What it will depend upon? Let us see. Number one, it will depend upon the amount of E. How far is the miscentering? Is the miscentering small or large? If it is smaller, this O dash point is somewhere here, then the value of E will be small. It will also depend upon the length of lines of sight. What is the meaning of this? The meaning of this is, if I draw a diagram here, let's say my original P and Q are there, this is O, and in one case, and now the miscentering is some amount here, and what we are doing, we are taking these as the line of sights, and there will be some error due to miscentering. Well, for the same P and Q, if the lines of sights are very, very long, and the same amount of miscentering is there, we take now the lines of sights from O dash, and then there will be E. So theta, and this is phi. So here in this case you will observe that the value of E, error due to miscentering, will be less than the value here. If I add E dash, E double dash, so E dash will be more than E double dash. So just by this graphical representation we can see, if the lines of sights are longer, the error in our angle due to miscentering is less. Okay? Anything else in which this error due to miscentering will depend upon? It also depends upon the direction. The direction means the miscentering could be in this direction, or it could be by same amount in this direction. Now it can be proved very quickly that the error in the angle due to miscentering will be more if the miscentering is in the direction of bifurcation of this angle. For example, in this direction, the miscentering error will be maximum in this case than in any other case. It can be proved very quickly. Okay, we have seen now two methods, method of repetition, method of reiteration, to measure any angle. What we can do, the angles which are there in the field, as we have seen, for example here, each of these angles we can measure individually by method of repetition, and also each of these angles can be measured by method of reiteration. Now what we want to see? We want to see in terms of accuracy, which of these methods is better. So for that we need to do a little analysis. And what we will do in this analysis, we will revisit some of the things which we had discussed in our earlier video lectures when we were talking about the error propagation. We will do one analysis here, how the error propagates from a simple thing to a complex thing, or in our final measurement. This is what we will see. So we will start with method of reiteration. Now in the method of reiteration, what we do, this is our P and Q, observer is here, and we measure this angle theta. How do we measure the angle theta? Theta is basically given by d2 minus d1. What is d2 and d1? We are taking a back side at P, we are taking the foresight at Q, and d2 and D1 are the averages. So I can write it D2 as sigma D2I. I will explain these terms in a moment by n, and as well as D1 as sigma D1I by n. Now why I am writing this way? Because here, as you see, theta is D2 minus D1, the average of all the four sides minus the average of all the back sides. This is what we do in reiteration, gives me the angle theta. Now what is a single back side or foreside? A single back side or foreside is when we are bisecting from O to P. What we are doing? We are doing two things. Number one, we are doing the bisection, and number two, we are taking the reading. We are taking the observations. Now how this bisection and taking the reading will introduce error? Because when I am bisecting, what is the meaning of bisection? For example, let us say if there is a tree, or maybe for, let us say there is a ranging rod here. Let us be more precise, because in case of tree, where to bisect will be something more of confusion. Let us take a case of the ranging rod. Now we want to bisect this ranging rod. So what we do? We put our field of view. This is the something which you are seeing through the telescope on the ranging rod, and we align our crosshair with the center of the ranging rod. So this aligning of the crosshair with the center of the ranging rod is the bisection. Now the question is, can we really align it? Will there be some error? Yes, we can never align it truly to the point or to the center of the ranging rod. So there will be some error because of the bisection. Second thing, once we have aligned it wherever, what we are doing? We are taking the reading, we are taking the observation. So while we take the reading through our graduated circle, what we do? We look through the verniers and try to see the reading. Again, this is also one more source of error. Whatever we read, we cannot read the true value. No, we cannot read the true value. So there are error sources because of bisection and reading. And these two errors can be estimated. Let us say the standard deviation for bisection error is sigma p square, and standard deviation for reading error is sigma r square. Now as we have seen, we have in the method of reiteration, our D2 is average of all the four sides. Now what is one foreside? If you look at one foreside, D2I, this I varies from 1 to n. The meaning of this is there are n number of observations of the angle. This angle we are observing n number of times. So there are n number of foresides and n number of backsides, and this is how we are determining this angle. So this I varies from 1 to n. Now in any single foresight, let's say in any single foresight, the error of D2I, the standard deviation of this is dependent upon and can be written as sigma r square plus sigma p square, because these two are the sources of error in taking the foresight. So in my foresight, these two are the error sources. So the standard deviation of the error for this foresight will be given by this formula. Now if it is so, what we are interested in? We are interested in finding D2, where D2 is the mean D2I by n. Now we have seen one formula. We have seen that formula is if y is fxi, we are computing this y from several observations, which are, for example, x1, x2, x3, so on up to xn. So in computing this particular quantity, we are making use of all these observations, and in all these observations there are errors: sigma x1 square, sigma x2 square, sigma x3 square, and so on. For example, we know these. So we have seen in the error propagation that how these individual errors will propagate into y, and this is given by, if you recall, sigma y square is sigma I is 1 to n, because there are n number of variables, and partial differentiation of this function f against each of these I, square of this, and multiplied by sigma x I square. Now this we have seen. Now what we will try to do, we will try to use this for this formula. Now if it is so, what we are interested in? We are interested in square. Now how do we find it? So the meaning is, if you take the note from here, we are going to differentiate now this d2 partially with each individual d2i according to this formula. So what it becomes? It becomes sigma d2 d2i square of this into sigma d2i square, and this I varies from 1 to n. Well, if you solve it, by solving this, you will find the value of this is I is 1 to n, and this total turns out to be 1 by n square into sigma d2i square. And if you solve it further, because the sigma is there, I is 1 to n, so that will become n by n square into sigma d2i square. Well, we can write it as 1 by n into sigma d2i square. If we expand this d2i square, we know the value of d2i square already. That's the value of the d2i square here. If you write that value there, what we can write now, sigma d2 square is equal to 1 by n sigma r square plus sigma p square. So that becomes sigma r square plus divided by n sigma p square divided by n, and that's my d2 square. Okay, let's look at this, what it is so far. If you are looking at this, then you will notice the sigma d2 square is the error which is propagated because of the reading error and because of the bisection error in the average of the foresight. Well, similarly, with the same, we can write also sigma d1 square as sigma r square divided by n plus sigma p square divided by n. Now what is the meaning of this? Because when we are taking the back side, that was d1, when we are taking the foresight d2, the things are same, there is no change. So if there is no change, the error which is propagated will be the same. Okay, this is still not clear because we want to determine our theta, and theta is d2 minus d1. Now the error which is there in d2, which is sigma d2 square, and error which is in d1, sigma d1 square. We are writing these errors in terms of the standard deviations here. How they propagate finally into theta. So in order to do it, again we will use what we had done for fxi, that particular formula we will use. Okay, in order to use that, we can write sigma theta square as, if we partially differentiate now this with d2 and d1 individually, we will find that it will be 1 into sigma d2 square plus 1 into sigma d1 square. So if you write it further down, because we know these values of sigma d2 square and sigma d1 square. So if you write it further, we can write it as 2 times, now from here, sigma r square by n plus sigma p square by n. This sigma theta square is the error in angle measurement for this theta in the case of the method of reiteration, and it is being given by this particular value here. Now what happens in case of method of repetition? If you look at the basics of the method of repetition, in the case of the method of repetition, our observer is here, point P and point Q. What we do? We first of all bisect P, the ranging rod there, and we bisect and we take the observation. Then, after doing several rounds of the instruments, because we are summing up the values mechanically, and then we finally take the reading here, take the reading at Q, while in between when we are doing these rounds, we always at every time bisect Q. So what we are doing? We are doing the reading, we are taking the reading only twice. Only twice. Twice means once at P and at last at Q, while we are doing the bisection. How many times we are doing the bisection? If for example there are n number of repetitions, we are doing it 2n times. 1 at P, because initially first of all we bisected P, and then we are going to the Q and again bisecting it, and again we are bisecting, and we keep bisecting that way. So all these bisections are involved. So 2n number of bisections, the total number of bisections are 2n. Now how it is going to affect our angle theta? The angle theta we write here as our final reading d2 minus initial reading divided by number of the iterations that we have done. Now how the error will propagate again in this case? Now in the case of the D1, what the D1 was? D1 is, we are taking a reading, we are taking one reading, only one reading here, and we are bisecting it. First reading, and then we are bisecting this one. So in the case of the D1, we can write it as the error in D1 will be sigma r square plus sigma p square, because D1 means the very first reading. Very first reading means we are bisecting this P, we are bisecting it once, and then we are taking the reading, and that's the value of D1, that gives us the value of D1. While in the case of the D2, what we are doing? In the case of the D2, for each D2, P and Q. So for this Q, what we are doing? We come over here, we bisect it, we again close the horizon and again bisect it. So one more bisection. Now again we come over here, one more bisection, we close the horizon, one more bisection, again we come over here, so bisection plus bisection, and finally after doing this for n number of times, we do our final bisection and the reading. So we are taking the reading only at the last, but while we are doing this bisection, we are bisecting P and then Q, then P, then Q. This is the procedure of repetition. So if it is so, in the case of the D2, the error will be sigma r square plus 2n minus 1 into sigma p square, because we have in order to take this D2, we have done only one reading while we have done the bisection 2n minus 1 number of times. Well, what we know, in the case of the repetition, the angle is given this way. Theta is d2 minus d1 by n. We know now the error in d2 and error in d1, how they will propagate in theta. So this is what we are going to see, because we know the error in d1 and error in d2. So error propagation in theta, because the theta we are writing as d2 minus d1 by n. So using again and sigma y square, we have done it I1 to n del f by del xi square into sigma xi square. Using this same philosophy, we can compute now for sigma theta square. And if you now differentiate partially this particular function against d2 and d1, what we will get? We will get 1 by n square sigma d2 square plus 1 by n square sigma d1 square. Now we put the value of d2 and d1 from here, sigma d1 square and sigma d2 square. Sorry, I should write it as sigma d2 square is sigma r square plus 2n minus 1 sigma p square. Now if I take these values here, so what I can do, I can write it as now 1 by n square, I take it out, sigma r square plus 2n minus 1 into sigma p square, plus for sigma d1. Sigma d1 square is sigma r square plus sigma p square. Sigma r square plus sigma p square. Okay, we solve it further now. In solving this further, what we will find? We will find this sigma r square and sigma r square, they will add. So we can write it further as sigma theta square as 1 by n square sigma r square, of course twice of that, plus 2n sigma p square. Now this can further be simplified as 2 sigma r square divided by n square plus 2 sigma p square divided by n, and this is what we get here. Now we compare this with the one which we got for method of reiteration. In that case we got I square by n plus 2 sigma p square by n. This is what we got in the case of method of reiteration, as you can see here. Now what is the meaning of this? Let's look into the meaning of this. In the case of method of repetition and reiteration, the error which is propagated into our final angle, that we are writing by sigma d square, the standard deviation of the error. In both the cases, it is dependent upon the error due to reading and the error due to bisection. The error due to reading and error due to bisection, similarly here. However, as you will notice, for the reading, the term here in the case of the repetition is n square, while in the case of the reiteration it is n. What is the meaning of this? The error propagated in theta is less in the case of the repetition because of the reading, because this term is square here and this term is only 1. So what does it indicate? This indicates because in the case of the repetition method we are taking very few or rather only 2 number of readings, the first reading and the last reading. So the error propagated in our final angle value because of the reading is less. So that means the angles which we compute or which we observe by repetition are better than the angles which we determine using the reiteration. Now this is very important, and this analysis is very important, and the steps which are involved in this analysis, you should do it yourself, then only you will understand all these clearly. Okay, so far we have seen the methods for measuring angles in horizontal. Now we will see the method for measuring vertical angle. Now what is the meaning of vertical angle? The meaning of vertical angle is, for any object we are measuring the angle of this from the point of observer with the reference as the horizontal line. So that's the horizontal plane. So from this horizontal plane we are measuring this angle to a object there. So that's my vertical angle. We have seen this definition. How do we measure this? Using the theodolite. So this is what we are going to see now with the help of theodolite. Now here in the theodolite, the procedure will be same, some of the procedures as in the case of the horizontal angle. First of all, we take this theodolite to a point where we need to measure the angle, because obviously whenever we are measuring the angles, we are measuring the angles at the point of the observer, some station. So we will take this tripod there, we will center it, we will level it. Now once we have centered it, leveled it, we will fix this instrument, the theodolite, on the tripod, and again we will level using these 3-foot screws. So the idea is to make this horizontal plate horizontal. Now this is horizontal. What it does, while we are leveling this instrument or the theodolite using these foot screws and making this plate bubble in the center, it also ensures that my vertical circle is also vertical. So this is important. Henceforth, I am going to measure the angles in vertical plane. I don't want to measure the angles in an inclined plane. I want to measure them in a vertical plane. So my vertical circle has to be vertical. Well, one more thing. Because in the case of the vertical angle measurement, that's the vertical circle and this is the vernier or the index frame. What happens if I rotate as we do here? If I rotate my telescope, what is happening there? In the case of the vertical circle, it starts rotating. With the rotation of the telescope, the vertical circle rotates, but the index or the verniers, they stay where they are. So these index or these verniers, they form a line which is the horizontal line or horizontal reference. So I need to ensure that this is also horizontal. How do we ensure it? We make use of the altitude bubble. We have seen on the index frame there is an altitude bubble. This altitude bubble is more sensitive than the plate bubble. So after centering this plate bubble, again using these foot screws, we center this altitude bubble. Now this is very interesting. I am saying the altitude bubble is more sensitive than the plate bubble. Plate bubble is in center. Now it is center wherever I rotate my instrument. Now I try to bring this in center. While I try to bring it in center, my plate bubble will not change, will not shift its position because it is more sluggish than this one. Well, once this altitude bubble is also in center, what it ensures? This ensures that my index is horizontal. Now at that time, when my index is horizontal, if I rotate my telescope in such a way that the reading over here in vernier A, generally for the vertical circle we say vernier C and vernier D is 0, 0, 0. If it is so, my line of sight should be horizontal. I repeat, because my index is horizontal now, I rotate this telescope in order to ensure what is happening. While I am rotating the telescope, the vertical circle is rotating against the vernier. I make the reading 0, 0, 0. We can make use of the tangent screws and the clamp screw in order to do this thing. So once that is ensured that the reading is 0, 0, 0 here, 0, 0, 0 here, sorry 180, 0, 0, 0. Then in that case, the line of sight, which you can see here, should be horizontal. Now in order to measure the vertical angle, what next we do? We sight to the object. Of course, we'll need to focus the eyepiece and focus the objective lens. So that particular object is bisected. Once that is bisected, whatever is the reading over here, now in vernier C and vernier D, we note down those readings. And these give us the value of the vertical angle. The vertical angle as defined here, the line going there, the horizontal line and the angle here. This we are doing right now for me in face right. So we repeat this entire procedure on face left also. How do we record these readings? We'll come to the slide here. Now this is the table for vertical angle measurement. The instrument, as in this case, that's the point where observer is. So instrument is at O. Our 2 points are P and Q, to which we have to measure the angles. So P and Q, that is the side 2. Right now we are taking the observations, for example, in face left. Now we are writing the readings here in degrees, seconds and minutes and seconds. So whatever was the value of the reading, we'll write it here. And this is for the another vernier, the vernier D. This is vernier C. And we take the mean of these. Mean of vernier C and D, we write the mean here, and that gives us the vertical angle. Similarly, we do it for Q, and it will give us the vertical angle for Q also. So vertical angle for Q, vertical angle for P. We can do the same procedure on face right. Again, you're reading the vernier C, vernier D, taking the mean and finding the angle. And then finally, the angle which is coming from the face left and the angle value which is coming from the face right will average these two. And we'll write the average of face left and face right. Similarly for Q also, average of face left and face right. So what we have done, this is what is recorded here is for any object P only one set of observation. We can repeat this multiple times depending how accurate we want to be in our observations. So this is how we observe the vertical angle. Now we have seen all these angle measurements. We are going to the another aspect, that what are the errors? Are there any errors in measuring these angles? What are the errors which may be introduced into the theodolite? So we will look into those errors now. Now in the errors in the theodolite, as usual, we'll talk first about the personal errors. How the personal errors will be introduced when we are doing the theodolite measurement. Okay, if you look at here, the observer, the surveyor, has not done the leveling proper. If the leveling is not proper, my horizontal circle is not horizontal. If my horizontal circle is not horizontal, what is happening? Now my graduated circle is inclined. So all the observations, all the angles which I am taking now, the horizontal angle, are not in a horizontal plane, rather in an inclined plane. Now this could be one error which can be introduced by the observer. Miscentering. We have seen the effect of the miscentering, what will happen. Then the bisection is not proper. We need to bisect the object properly. So the bisection is not proper. Again there may be error. Error in the parallax. If the parallax is not removed, we have seen how the parallax can be removed. If the parallax is not removed properly, again that will lead to the error in the theodolite because of the surveyor. Finally, while he is taking the readings, he is not taking the readings properly. Again, this is also a source of the error. So these all are the personal sources of the error. Similarly, the natural errors, there may be many. Some of them, while we are working in the field with the theodolite, it might happen if the ground is soft, one of the legs goes down. So what will happen? The leveling will change, and now our observations will be wrong. Or if it is too windy in the ground and there are vibrations in the instrument, again the readings which are taken will be wrong. Or maybe the refracting index of the medium. Many times in the summers, you will see when you are looking through the theodolite or the telescope, you will see there is a shimmering effect. Your ranging rod will appear to be shimmering. So it becomes very difficult because of the natural condition. Bisection of the ranging rod becomes difficult. So that also leads to the error. One more error. For example, let's say the sun is on this side here. So only part of the instrument is being heated. Now if only part of the instrument is being heated, what will be the reason? What might happen? The graduated circle may expand in one part, while it is not so in the other place. So again that might lead to some error. Also, that's my bubble tube here, and the sun is shining from here, the sunlight is falling on the instrument. So only part of the bubble tube is being heated. Because of that, the bubble will not remain in center, it will go out of the center. While we might construe it that the leveling has changed and we will try to level it. So in effect, what is happening? We are changing the horizontal circle. It's not anymore horizontal, we are changing it to be inclined. So because of these natural conditions also, there might be several errors which might be added into the instrument. Finally, the errors due to instrument, which we say instrumental errors. Now before we get into the instrumental errors, we need to understand couple of fundamental lines of the instrument. These are very, very important. We have understood the construction of the instrument, how it is made and all these things, but we need to look into some of the fundamental lines in this instrument. Okay, when you are talking about the fundamental lines of the theodolite, you have to follow the instructions or what I am showing you here very clearly, because that will make you understand what these lines are. We start with the vertical axis. If I rotate this theodolite, it is rotating about an axis which is the vertical axis of the theodolite. So we can show this as a line here. Then this is the horizontal plate and the axis of the bubble tube. If I show this in the diagram, this is the horizontal plate and that red line is the axis of the bubble tube. There is some relationship. The relationship is the horizontal plate should be parallel to the axis of the bubble tube. They should be parallel to each other. Then as well as these two should be perpendicular to the vertical axis. As you can see here, these are perpendicular to the vertical axis. Then further, we have now two axis systems in this part of the instrument. One is for the upper circle or the vernier frame and the other one is for the bottom plate. Now these two axes again should coincide, as you can see here by the dotted lines. That's for the inner one and that's for the outer one. So these two should coincide. If you go further up, the line shown here is the horizontal axis. What is this? Now in this theodolite, if I rotate my telescope, it is rotating about a line here. This line we say the horizontal axis or Trunian axis. So this is the horizontal axis or the true-linear axis. Is there any relationship between vertical axis and this horizontal axis? Yes, they should be perpendicular to each other, as you can see here. Well, we go further up. This blue line is the line of sight. So the line which is passing through like this. If I rotate it, the line of sight is rotating, as well as there is one more line which is shown here by the dotted one. This is the line of collimation. Ideally, the line of collimation and the line of sight should be coinciding, as well as these should be perpendicular to the horizontal axis and the vertical axis. For example, here, if I rotate it anywhere, the angle formed by line of sight to the horizontal axis is 90 degrees, as well as the angle formed by the horizontal axis with the vertical axis is also 90 degree, or we can say this way. So these relationships should be maintained in the instrument. If you go further up, we have the vertical circle. That's the vertical circle. Now the relationship of the vertical circle is, this vertical circle should be perpendicular to the horizontal axis or true-linear axis, and we have the altitude bubble. So this altitude bubble is in such a way that once this altitude bubble is in center, the line formed by the index of verniers should be horizontal. So this is what I am trying to show you here by this diagram. So these all are the various lines of a theodolite, which we say fundamental lines of the theodolite. So what we have seen the interrelationships of these lines. When we discuss further about the theodolite, we'll look into these lines again. So what we did today, we looked into the method of reiteration. We compared the method of reiteration with method of repetition for their accuracies. We saw how to measure the vertical angle. And then finally we have seen now the fundamental lines of a theodolite, which we will again repeat in our coming lectures. Thank you.